This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you my new project, and this new project is a DC power meter. As you can see, I have these small PCBs and the stencil already prepared. So I'm going to show you how I built this, and I'm going to test it, and then I'm going to show you the source code which runs everything. So this is the PCB I designed, and you can see that it is a relatively small PCB. The x-axis, or the wider edge, is 55 millimeter long, and the height, or the narrower width, is 45 millimeter. So it has a relatively small footprint. Therefore, it will be hopefully easy to integrate it in your project. And I designed this size specifically for a certain display. Unfortunately, I still haven't received the display, but I actually designed this in mind that this can be used with several displays, and I will show you how. So nevertheless, I can still build this thing. So what we have here is that this PCB is driven by an ATtiny85 microcontroller, and then it communicates with an I2C display. That can be any of the I2C displays that you can write code for, but I will develop code for two specific displays. You will see it later. And then the whole thing is then basically driven by a INA238 power meter module. And then I will show you from a closer perspective. I found a very cool shunt resistor which will do the job for us, and then basically make us possible to measure the current and the voltage running through a power line. And then at the bottom of the display we also have some let's say power part. The PCB can be powered in two different ways. If we have high enough voltage, then we can directly use the power line that we are measuring. So we tap into that line, and we use this buck converter to convert the whatever voltage here to 3.3 volts, or we just don't connect to the power line, and then we use an external 5-volt source, and I will show you how you can choose between these two. And now, as you can see, I have the PCBs together with the corresponding stencil, so this will allow me to apply the correct amount of solder paste everywhere, so I can build the PCBs much more easily. And as usual, all these components were provided by the sponsor of this video, PCBWay. Please visit their website using my link in the description. You can end up on their website directly, or you can follow my project page. And then if you want, you can order this PCB with the corresponding stencil, and you can replicate my project. And then you can have your own power meter module. So I hope you will use and like their services. And now let's get back to the video. So now I will populate one of these PCBs with the parts, and this PCB will be just used as a template. So I will know which part belongs where. And then I will take another PCB and apply the solder paste on the corresponding places using the stencil here. And then I will pick the parts from this PCB here, and then put it on this PCB, on the other one which has the solder paste applied on it. And then it will be easy to solder it. So then I will show you some close-up videos just to see how the process is done. So here is the product that I made. You could see it in the video. And this is how I imagine it, or at least one of the versions. So if I remove this, you can see we have our small tiny 85 microcontroller. And then I put a button directly here, but it's not necessarily to use it like this. Here are the 2 pins for the extra available pins from the microcontroller. So you can use this if you want. And then here is the power sensor INA238 module, and this is the shunt resistor. And I want to notice here that the footprint and the 3D model for KiCad did not exist until I made one. I mean, it did not exist on the internet, but I uploaded it to Snap EDA, so you can get it from there if you need it for your KiCad. And you can see that I managed to model the footprint properly because it exactly fits the real-life model. And down here we have a buck converter because the whole system can be powered in 2 different ways. You can see that there are 2 jumper pins here, and one is occupied here and the other is free. So how it works is the following. When I put a jumper here, that shorts this positive rail to the buck converter. So basically the device is self-powered, and by that I mean that whatever line you are measuring with this power meter, that line will power this buck converter, and then of course it will provide the 3.3 volts to the rest of the circuit. But in that case, we have to make sure that the voltage in the line is always at least, let's say, 5 volt or more. We have to check the specifications of the buck converter. So I will put it somewhere on the video, what is the minimum voltage that we need to have. But otherwise, it works well. And then if you remove this jumper pin, then the connection between this line and the buck converter is broken, and then we have to provide an external 5 volt. So for example, we can have a power bank or something which provides 5 volts, and that powers the buck controller or converter, and then that will provide the 3.3 volt to the rest of the circuit. So it provides it for the microcontroller, for the power meter chip, and for the display. So that's how it works, and I have to emphasize that when you directly feed the buck converter from the line, then these pins, the 5 volt pins, also become powered, because the 5 volt and then this pin, the left hand side pin in this jumper connection right now, is connected together, because that's how it made sense to me. So then you should not connect any 5 volt or anything to this when you power it from the positive line from the load side. And then you can see, I will try to find a tool to highlight this better. You can see that I made a small correction here. A wire comes from these 2 pins. These are the A0 and A1 address pins of this power meter chip, and they go to the ground. So the thing is that I accidentally made them no connect on this specific PCB, and therefore there was no address assigned to the chip. But you can see that with an easy fix I made it possible to address the chip. But I already updated the design, and I just basically connected the A1 and A0 pins together, as you can see it here, by soldering. But I designed a new PCB here, which connects these 2 pins, and then there is a via which directly brings everything to the back panel, which is the ground. So then the A1 and A0 pins are tied to the ground, as they should be when I want to use a specific address for this device. So that's that. And then then basically everything should work, but there's a catch, and that's another point. That's not my mistake, but it's more like specific to these displays. So you can see the pin layout of this display from left to right. We have ground, VCC, clock, and data line. And I designed this in a bit different way. I try to put this together in a way that you can read everything. So you can see that I actually made two different connectors here. The top connector is data, clock, ground, VCC, and the other is the mirroring image of it. So VCC, ground, clock, data. But then this is a third type of display. So as I mentioned earlier in the video, I have some displays ordered from China, but they still haven't arrived. But despite that fact, I wanted to make this video. And those displays have this one of these two layouts, because I have a large display which is almost exactly the same outline as this PCB. So then that would cover everything, and then of course we could not use these connectors. But then this inside would fit my other type of OLED display. So it looks exactly like this, but it has the corresponding pinout here. So VCC, ground, clock, and data. But here you can see that the ground and the VCC is flipped. So I cannot use it with this display, but I can demonstrate it. I just use some jumper wires to connect to this display. But yeah, if you go to my website, you will see the specific products with the affiliate links, and they will lead you to the correct displays with the correct pinout. So don't worry about that. And then, and basically that's all. So now I will wire up everything, and we will test this display if it works, and we will see how it works. So I wired up everything, and I just quickly explain what is happening here. So I have a power supply cable coming in to this multimeter, which is used as a current meter, and then the wire comes out and it goes into the positive side of this shunt resistor, or the high side. And then the current, of course, passes through the shunt resistor, and it goes to my test load, which is a 6 ampere Peltier cooler. And then just to complete the circuit, probably it makes more sense to explain it like that. So the black wire comes back to the negative side, and then that goes back as a black wire directly to the power supply. So then this is in series with the load and also with the shunt resistor. So this should measure the same current as the power meter device measures. And then I will use this device as a voltage meter. So I have my probes, and we will just poke around at different points just to see what is the voltage at different sides of the circuit. And then just to remind you, I'm using this board in a self-powered mode, which means that it is taking the power from the same voltage which is supplied to the load. So then that power powers the buck converter, which produces the 3.3 volts for the microcontroller, for the display, and for the power meter chip. And then we will measure how that 3.3 volt looks like as well. So now I turn on the power supply, and then we see different parameters here. The display already shows some details. I will try to zoom in. So there is a small message that you can see. Probably it's more visible if I put some shade on it. And it needs some time to start up, because I set it up in a way that it does a lot of averaging and stuff. So we will get rather reasonable numbers. But in the meantime, I can, for example, measure the voltage on the 3.3 volt. So I will try to do that now. So this is the ground. So that's our 3.3 volt that you can see on the left hand side here. 3.3 volts. That's very nice. And we can see that now we have some data showing up. I will show you from closer perspective in a moment. But I want to check the voltage. So we have 6.8 volts, 6.811. Let's do it like this. And then here on the power characteristics, so this chip has a built-in thermometer, and that's what you see on the top. Probably it's more visible like this. So there you see it's 24.5 degrees Celsius. Then you also see the voltage, 6.816. And this guy here measures 6.814. So yeah, close enough. And then the current is 1.698. Well, 1.683. So close enough. So 1.689, 1.680, that's close enough. And then of course the power is calculated from the product of those two. So 6.819 times 1.681, and that's the 11 watts. So that's what we get on our Peltier cooler. So now I change the voltage a little bit. Let's say now we have 7.8 volts. So of course this needs some time to update, but it will soon update. And now I see 7.934. My multimeter measures 8 watts. Also here it's 7.9. Now I also measure 8.25, and this is 8.025, and this is 8.05. Close enough again. And then the current 1.986, and then the current here is 1.989, and then 15 watts. So that's that. So you can see that it works pretty well, and it does what it has to do. So it works like that. And once again, the display will be in the center here, so it will look much better. But you can see that we can use this very nicely. So I just turn on the power supply, just not to heat this Peltier cooler anymore, because it's only passively cooled. So now we have everything shut down. And basically that's it. So you can see that we have this nice power meter module. Actually, I built one more so I can show it from a closer perspective. So this is the final product that you will see, plus the display. So if you use this OLED display, then the product will look like something like this. And why I designed it like this, once again, the original outline like this, that matches a display that I want to use for the, let's say, final version. So then I can make a small enclosure, and this can be like inserted anywhere in a circuit that you want to monitor constantly. And then you just look at the display, and you see the characteristics. It's very useful if you have something like a battery module or something and you want to just look at it. But if you use it with this display, then you can see it sits there nicely. Then you can have these banana plugs, or these kind of banana plugs, just screwed in. These are M4 holes and pads. So that's very nice. And of course, once again, on the project page where I share the project, this mistake is now fixed. So when this video is uploaded, the correct file is there. So yeah, in fact, when I'm recording this video, I haven't even uploaded anything to that project page. So I'm 100% sure that the correct file is on my project page. And then one might ask that what happens with high currents? Well, nothing bad. I calculated the power dissipation or heat dissipation of the traces, and I'm using 2 ounces instead of 1 ounce's thickness. So it should be enough. And you can see here, I rated it for 15 amps max, but actually for like little periods or short periods, you can use 20 amps with this. The shunt resistor is selected for 20 amps, but 15 amps is, let's say, that's safe, more safe. But 20 amps is also possible. So yeah, this is how it will look like. and it will print everything nicely on the display. And you will see this device in many of my future projects, because I really need to monitor power in some applications. So yeah, you will really see it in those projects. And now, of course, the last part that we need to go through is the code for this tiny guy. It's just a few hundred lines, so it will go quickly. But yeah, I developed the code for this ATtiny85, as you can see, because it works. So let's see how it works. And also in the future, I think I will write a library for this specific power meter module, because I had to figure out everything by myself based on the datasheet, because I did not find any libraries for this. But it's a simple I2C communication, so it's not a rocket science. So let's head over to my computer and let's see the coding. So this is the Arduino code, and let's see how it works. So I'm using an ATtiny85 microcontroller. So I'm using this core for it and libraries. So you can find that in the board's manager easily. And then I'm using I2C, so then I need this library for it. And I'm using the SSD 1306 OLED display in this code. So I'm using the Tiny 4K OLED library. And then when I was developing the code, I used the I2C scanner to get the address for my two I2C units, which is the power meter module, this guy here, and the display. So I just noted it down here. It could be different for your case, so always check them with an I2C scanner. But for this demonstration, these are the codes that I might need. So to save space, I always tried to declare the variables locally, but the max current is used throughout several functions, so I made it into a global variable. And as I said during the demonstration, in short periods, the board can withstand 20 amperes without any issues, and the shunt resistor also sized for that purpose. So that's what I use here in my calculations, but again, please use 15 amps maximum if you want to run it on a long term. So then we initialize the display in the setup. That's what you see in line 12. 128 horizontal pixels and 64 vertical pixels. So that's what we have here. This is how we initialize, and then I clear the display because sometimes the display has garbage from the previous session, or it has some built-in welcome screen or something. So that's cleared in this line. And then I set the font to this font size. This is a larger font size because then I want to print some welcome display that you can see here. Nothing fancy, just some text. But one thing I want to show here is that the set cursor function works in a very funny way. So the first coordinate is the x, which is along the horizontal axis. And that works as you would expect. So one value extra or one additional value, if you increment the number, so make this 1 or 2 or 3, that will be the number of pixel. But when you use the second argument here, which is the y coordinate, that is not measured by pixels, but it is measured by line number. So if you enter, let's say here I entered 6, that is not the 6th pixel along the y-axis, the vertical axis, but it is the 6th line, or more precisely the 7th line, depending on the font size. So that's that. I set it up like this, and then after printing the welcome message, I wait for 5 seconds to let everything settle, and then I initialize and configure the power meter chip. And I will show these functions, of course, how they work. And then I clear the display, and then I print the permanent text on the display. So on the left side, you could see that there was different kind of text for showing you that this line is for the temperature, the other is for the voltage, and so on and so on. And then that's done here. They will never change, so I can print them in the setup part of the code. And I just counted the number of characters, because then when I place the cursor for the values, then this will be easy to look up and follow. And then in the loop, I run 4 different functions. I read the die temperature, that's the temperature of the chip. And that is also good to use to follow if the PCB gets hot, because the chip is relatively close to the shunt resistor, and of course all the current runs through that, so it will locally heat up the PCB if the shunt resistor gets hot. Therefore it will have an effect on the chip, and you will see this in the values when you read the temperature, because then you will see that, okay, this function gives you back increasing temperature. So then after each function I leave 0.2 seconds delay, and then I jump to the next function. So I read the bus voltage. So that is the voltage basically which goes to the load, and then I read the current, that is the current going to or through the load, and then the power, which is calculated from the bus voltage and the current. And then I wait 1 second here. I know delays are not the best, but for this demonstration and for this very simple thing, I can use them, because I don't really need to do anything else when the code hangs here for a certain period of time. So then we have the set configuration. So again, refer to the datasheet, but I just copied out the most significant things here. So this is the contents of table 7-5. What we have in the datasheet is clearly written, but actually I'm using everything as default. So all my bytes are 0. I even wrote here that, yeah, they are all 0. So then that will go to the register. So then we have to send these numbers or these bytes to the chip somehow. So I wrote a separate function for that, and then what is inside it, it shows up here. So the first parameter here, you can see that's the register address. So that is the address of the register on the device. And then we have the address of the device, which is simply the I2C address. And then the configuration data is basically, or config data is the configuration data that we want to write, and that is the 2 bytes, which is now just all 0, so it's 0. So that's what you see here. And then set ADC. Again, please consult the datasheet, but I just put everything here. And then I selected my own parameters. So that's why we had to wait in the beginning after the welcome screen showed up, because these different conversion times were a bit long, but you can see here at the end what is my chosen values. And then based on that, I just created my own 16-bit number, and then I converted it into decimal number, and then just simply sent it to the register number 1. So again, the same strategy as you see here, and then I just filled in the corresponding numbers. So it's simple. Then again, check the datasheet. But yeah, the datasheet has a set of equations which is used to calculate this shunt calibration parameter. So then you get the current and the power calculated properly. And then for that, I'm using this specific product. This is the code, so if you Google this, you will see it on Mouser or DigiKey or these trustworthy sourcing websites where you can buy this specific shunt resistor. And I picked a 2 milliohm shunt resistor, and if I remember correctly, it is 5 watts, so it can dissipate enough power. So I just declared the variable of that, and then we have to calculate the LSB, which depends on the resolution here, which is 2 to the 15th power. So I guess it's the resolution of the AD converter, 16 bits minus 1. That is the exponent here. and then the max current is 20 amps. So then the 20 amps divided by basically the resolution or something like that. That's what I assume. And then the shunt cal is a parameter which we calculate based on this number provided by the datasheet. So it's basically this number here, which I highlight now. And then the previously calculated LSB and the value of the shunt resistor. So this is from the datasheet. And then I substituted all the numbers and calculated it by hand, and this formula exactly gives 1000 for my case. So when I use 20 amps here, and I use 0.02 ohms of resistance as the shunt resistor value. And then I just have to pass this to the register number 2, and that's that. So now the chip will know what is the conversion factor. And then I just made a bunch of functions to get certain voltages. I'm not using this, but I implemented this. So this is the shunt voltage. So this is the voltage drop across the shunt resistor. Actually, the device measures this because this is how it can calculate the rest of the parameters. I don't need it, but I just implemented the function, and I can explain how it works. So the shunt voltage is calculated by the response read from the from basically the device. So this is how it's read. So from the register number 4 we get the value, and then we have to multiply that with a certain multiplication factor based on the resolution or range that we chose for the ADC, and you can see it here, and you can also see in this table. If you go to the table, you will see that if I chose ADC range equals 0, then I have to use 5 microvolts for conversion factor. So that's what is here, because that's how I initialized my ADC. But if I use a different ADC range, which is higher resolution, but smaller range, of course, then I have to use this as a multiplication factor. So 5 would become this instead. But let's leave it like this. And then the bus voltage. This is the voltage difference across the positive and the negative side on the board. And this is the voltage which is fed to your load as well. And again, we have a conversion factor which comes from the table of the datasheet, and then we just multiply this with this guy, and that's all. So that's done. And then I made a format voltage function which will take the voltage in, and depending on the magnitude of the voltage, then it will return it in millivolts or volts or microvolts even. So you will see how the formatting works. Then the temperature. So here I created a temperature array because we cannot use floating point numbers directly. We have to convert them into something that can be printed on the display. I use this practice quite a lot in my projects, so this might be familiar if you have been following my videos for a while. So I take the temperature calculation. Again, we have a conversion factor for the LSB. So 1 LSB or 1 bit is 0.125 degrees Celsius. So I just have to multiply my reading from the register with 0.125. And you can see that I do a bit shifting here, because if you look up the table, the 3 to 0 bits, so those 4 bits, 0, 1, 2, 3, are not needed, but they are part of the number. But if we shift out our 16-bit number towards the right with 4, let's say, positions, then we only keep our useful or usable number in that 16-bit, let's call it box, and that will become our value, our temperature value. So that's why I read the response from the register number 6, and then I shift out these 3 to 0 bits, and then I just multiply it with 0.125, and then that becomes the temperature. And it works. I tested it and it works quite well. So again, we use this D2STRF function, which is now highlighted here. So what we have here is that the function takes the temperature reading, and then we have to determine or define that we want to store it on 5 sized array. We want to store 2 decimal digits, and we want to put the conversion value in this temperature array. So this will be an array of characters which will basically store our converted floating point number. And then I just move to a certain position on the display, erase the previous part, move back to the beginning of that printing area, and I print the new text. And that's all. And since I know that I will also need the unit, I just move a bit further towards the right side of the display. So that's why I place the cursor here, 112. I stay in the same line, so you can see that the Y is 2 here. I erase the previous one, which actually would not be necessary, but just to be sure, I clean that, and I print this space and then C. So that will show us that the unit is in Celsius. And then we read the current. Again, this is just some formula that I have taken from the datasheet. I just use the formula, and then I pass the calculated value to this format current function, because I can have microamps, milliamps, and amps, and I want to format my output, because if I want to, let's say, show 5 microamps, I don't want to print 0.000 and so on 5 amps. But then I can just say I print 5, and then I write the unit microamps at the end, and then it looks much more neater. And then power is the same. So I have this formula from the datasheet, and then I just simply pass it to the function which formats the power. So then we come up to this part, which is the write register. So whenever we want to communicate towards the chip, this function that we use. And here you can see that this is very similar to the wire library, so to the I2C communication, but it uses a bit different words. So instead of begin transmission, we have the start, and instead of end transmission, we have the stop. But it's basically the I2C or wire library, but with a much more lightweight version. So start reaches out to the device. So that's what we do here. So I have the I2C address here, which is based on the A0, A1 pins, and I tied them both to ground. And then I just take my data. So I have the config data, which is passed by this parameter. And then first I shift the config data to the right by 8, because I just want to send the MSB first, and then I just leave the rest as it is and send it. So I send the 2 bytes separately. And then I just stop the transmission, and then I just wait for 10 microseconds. And that's all. And here we can read the response, and I made this read response underscore 2, because here I want to indicate that I'm reading 2 bytes, because there will be another function, you see it here, which reads 3 bytes. So I wanted to distinguish them. And again, it's very simple. We reach out to the chip, and then instead of the request function, we have a restart function. So another difference between this library and the wire, the original Arduino wire library. We want to request 2 bytes from this device address. So I create a 16-bit variable, that's the response. So first I read the first 8 bits, and then what happens in the next line is that I shift it to the left, so between 15 or yeah, it depends on how you number, but if you start numbering from 0, then 15 down to 7. We store those bytes, and when you download the code, you will see how it's explained. But we shift these 8 bits to the left. So the first 8 bits will be all 0, and that will be free. And when we read the next byte, so the next 8 bits, they will just they will be put in those available first 8 bits, and then these two numbers are combined together. So basically we rebuilt the 16-bit number, and then this function returns with the response, which is just the 16-bit or 2-byte value read from the register. So then this is the function for the 3 bytes, and if you follow my videos for a long time, you could see in the ADS1256 video that this is basically the same strategy, because there I also have to read a 24-bit number, so I do the same here. So this is the same as the previous, so I'm not explaining this, but yeah, we just communicate with the chip. And then I created a 32-bit variable here. So then I occupy the first 8 bits by reading the first byte. So from 0 up to 7, all the bits are filled in with the reading. And then I shift that up. So now it's between 8 to 15, so 1 byte up towards the left. And then I read the next byte and combine it with the already shifted value. So now I have a full number between 0 up to 15. So that is 16 bits, and that is our number. And again, I shift this whole thing, the whole package between 0 to 15 left. So these 16 bits now will be between 23 and 7 or 8, depending on how you look at it. But yeah, the first 8 bits are not occupied, and from the 8th bit up to 24th bit we are occupied with the reading. And then the final byte is read and then combined together with the already existing 16 bits. So now the whole number is then filled in from 0 up to 23. So that is 24 bits. And then we just return with this response wherever the function is called. And now we have this format voltage function, which I showed previously. So we take the voltage in and we represent it with the proper units. So we know that the default unit is millivolts, because if you remember, the LSB multiplication factor was also in millivolts. So whenever we get a raw bit reading from the register, we have to multiply it with a voltage conversion factor, which is represented in millivolts. So our reading will be in millivolts. And then I just have a bunch of variables, which is just the formatted voltage, and then the voltage unit. This will just help me to follow with the units that we selected. And then an array, because we have to print the float on the display and it cannot be printed as float. It's the same explanation as previously. So then if the input voltage is between 1000 and 0 basically, or smaller equal than 1000, because we are in millivolts, then we know that we want to represent the voltage in millivolts. Because, for example, let's say I want to print 25 millivolts. It looks better to print 25 point something something instead of 0.025 something something, and say that it is in volts. So let's say then we know that we want to have our voltage in millivolts. So actually we don't change it. So the formatted voltage becomes the input voltage, because the default unit is millivolts. And then I just indicate the code that I'm using the M here, so it's in millivolts. And then if we are above 1000 millivolts, then we print watts. But we know that our unit is still in millivolts, so we divide it by 1000. And it is shown here on the example. So the 3456.76 millivolts becomes 3.45676 volts. That's how it will be formatted. And the voltage unit is now watts. So then I do the conversion, and print it on the display. This doesn't need any explanation because I explained how the D2STRF works. And then I go to the place where I want to show the unit, so that's almost the rightmost part of the display. And then if the voltage unit was selected to be millivolts, then I print millivolts. Otherwise, I will print volts, and that is like, yeah, equals 1 or like this. And then the rules for the current is the same. So the first thing is that we have to say that the default voltage is in amps. That's how the device sends the microcontroller the units. So I just wrote that here as a notice. And then this is also the same as I did with the voltage. So then we know that we have amps as the default unit. So if we are below, or maybe this can be also equal, if we are below or equal 1 milliamps, then we want to use microamps. So that's what I wrote here in the comment. So then the input current first is multiplied by 1 million, and that will be because I don't want to show 0.00000 something, but I want to show, let's say, 20 point something something, and then put the unit after the number. And that's what will happen. So then I let the code know that I'm using now the micros, and then that's that. But if the input current is between 1 and 0.01, and now I see that the equal signal is here, so I just remove this symbol. So if we are between 1 amp and 1 milliamp, then we use the milliamp units. And of course that is one prefix up, so it's not 10 to the minus 6, but 10 to the minus 3. So then if we want to represent it with like proper numbers, we just multiply it by 1000 instead of 1 million. And then we let the code know that it uses millis. And then the rest, so whatever, then we keep the current in ampere units, and we let the code know that it has to use amperes. And then again, we print the number as it is with the fresh, let's say, conversion that we did in this line. And then we move to the rightmost edge of the display, and then print one of the units depending on this, or this, whichever is selected. So that's that. And then finally we have the power that is by default in watts. We have our variables that is needed. So then if we are in the microwatts region, then again we do it similarly as we did in the current. So we multiply it by 1000 or 1 million, sorry. And then we know that we want to use microwatts. If we are in the milliwatts region, that is expressed here, then we just multiply by 1000, and we let the code know that it's in the millis region, and otherwise we are in the watts region. I don't care about kilowatts because that is it's achievable by the board. For example, if we run something at 50 volts and 20 amps, or even higher voltage and a little bit less amps. But yeah, if you want, you can implement it. You see how it's done, so you can probably modify the code. I will not run anything in kilowatts with my power meter, so I did not find it useful to implement it. So then, yeah, convert it into character array and print it on the display, and then also print the power unit. And then I have a final 4 lines here. For some reason, whatever I did, I could not get these values for the power and for the current printed on the display. I had the C letter for the Celsius, and I have the MV or V for the voltage. So those worked, temperature and voltage units were always printed, but for some reason the current and the power units were never printed, except I found this workaround. I moved to the final line, and I have to call this specific variable. So I just cannot print a random garbage anything on the display, but I have to call the unit, the power unit. And then if I print the power unit, then the units on the display will show up for some reason. I don't know why. So what I do is that I just print the unit and then I erase it, so it's like I haven't even printed it, but from the program's perspective it does something which makes it show up. So if you see the bug in my code, please let me know. And then yes, basically this is the code for the ATtiny85 microcontroller and for my custom made DC power meter. So if you want to get this code, I want to emphasize that you can support me on Patreon, and if you go to my Patreon site, you will find this code there available for download if you are a supporter, and then you can play around with it as you wish. Otherwise you just bear with me and follow this video and then copy the code from the display. Then also don't forget to visit my project website on PCBWay's page, because then you can order this PCB if you want and you can build your own tiny power meter. And I think it's a very useful tool because it's a tiny tool and you can build into separate parts of your circuit, so you can investigate the different power rails in a DC system. And this chip is also relatively flexible. It can detect a quite high voltage, 85 volts maximum, and because the way I chose the shunt resistor, it can also go up to 15 amps or 20 amps if it's just a momentary current. So then yeah, it works pretty well. And also don't forget to visit my website, because I put some extra resources there, some pictures, some more explanation about how the circuit works and why I built it like this. So maybe that article will be also interesting and useful to you. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.